Okay, so welcome everyone to this talk. So I will talk about introduction to quantum circuits, and so my own background is in computer science and mathematics, and sort of that's also the perspective I will take in this talk, but I'm aiming at a very broad audience. So basically, as long as you know some very basic linear algebra and some very basic logic like and, or, and not, then that should be enough to understand this talk. In some sense, I think if I remember a long time ago, I was reading, I think Richard Feynman has some lectures on computation, and I think it's maybe a little bit like that. He was trying to sort of learn computer science and sort of see how it connects with physics, and maybe this is a good reference if you want to read up on it if you come from the physics side. Okay, so I'm part of QSoft and University of Amsterdam. Okay, so here's a quick outline of my talk. So first I will talk about logical gates and circuits. So basically one of the main things I want to explain is how to implement any Boolean function. So basically any function that just takes some zeros and ones. So you take a string of n zeros and ones and you just want to map it to either 0 or 1. So you can imagine this is maybe an encoding of a picture, and this is saying, is that picture a cat or not? So then I will explain how this can be done, and then how to make this reversible. And then to connect this with quantum computation, I think the most helpful thing to do is to look at probabilistic computation. So basically this notion of probabilistic bits is sort of the simplest thing you can imagine, that is kind of like a qubit. And then I will explain what the quantum bits of qubits actually are. And then I basically will give a kind of a quantum counterpart of this result that you can implement any Boolean function in principle. So I will show how you can, in principle, implement any quantum operation. And you'll see later what it means more specifically. And if you have any questions, just feel free to interrupt me, because the audience is quite small, so I just want to make sure you follow and understand what I'm saying. Okay, so let me give a quick overview of the logical gates. I mean, if any of you have programmed, you probably are familiar with these. And okay, so basically, so let's say, so these gates here, they have two inputs and they have one output, and these inputs are going to be just a pair of bits. And the AND gate is simply, it's always 0, except it's 1 if both inputs are 1. So if this is 1 and that is 1, then you get 1. That's why it's called AND. So for the OR, it's going to be 1 if at least one of the inputs is 1. So so it looks like this, the truth table. And XOR, which is called exclusive OR, it means that exactly one of the inputs should be 1. So basically, if you have both of them 1, then that's actually 0. And the rest looks kind of the same as OR. So I guess in English, maybe sometimes there's a bit of confusion which one of these we mean. But so this is kind of like, that's why it is called OR, and this is called exclusive OR, just to make the distinction. All right, so then, and this one is very simple, it's just negation. The NOT gate has only one input, so you just flip the bit the other way around. And so this gate will also be very useful. So it has two inputs and two outputs. And so it's called controlled NOT, because the idea is that we're gonna, so this is gonna be the control, and this is the target. And so the idea is that we want to sort of flip this bit if this bit is 1. And so first of all, nothing's going to happen to the first bit. So what comes out here is going to be the same. So this is the first bit. And the second bit is going to be flipped if the first bit is 1. So here the first bit is 0. So the second bit, this Y, is not affected. It just comes out the same. And then here the first bit is 1. So that's why this should be inverted. So we get 1, 0. So that's the sort of the operation of this control NOT gate. And so now we want to use these kind of elementary building blocks to make more complicated functionality. It's kind of like, imagine these are small subroutines and you want to just kind of plug them together. All right, is there any question about this? Or? All right. So it's useful to represent these operations sometimes by some mass, and so let me just write quickly down how you could do this. So for example, here, since we're working with zeros and ones, you can imagine that you can try to represent these gates basically by addition and multiplication of 0 and 1. And so that's what the Boolean algebra is about. So the NOT gate is just flipping the bit, and it's kind of like adding 1. So you can imagine that this NOT function is just, so I will use this plus with a circle to just make sure that this is basically, so this is the modulo 2 addition. And so the only thing you have to remember by working this modulo 2 is that 1 plus 1 is 0. So everything else, you know, addition and multiplication is the same. So the only symbols you have are 0 and 1, and you add and multiply them in the usual way, except you have to use this because, you know, normally 1 plus 1 would be 2, so you have to make it 0, so you don't get out of this, this set. Okay, so then the negation is just the same as adding 1, basically, because it maps, if you have 0 and add 1, you get 1. And if you have 1 and you add 1, then because of this rule, you get 0. So then the XOR is just adding the 2 bits together. So if you look at this table here, you know, it really, this is exactly what's happening. So you're just adding these 2 bits together to get this, and then this is the special rule, then 1 plus 1 is equal to 0. So the XOR corresponds to addition, and just corresponds to multiplication, because the output is 1 exactly when both of these are 1. So if you look at, again, at the truth table, so if you multiply these numbers, you always get 0, except when you multiply 1 and 1, and then you get 1. And then this CNOT has 2 outputs. So the first bit, this control doesn't change, it just comes out the way it was. So this is just X. And then the second bit gets flipped if the first bit was 1. So you basically need to add to the second bit, which was Y, you need to add the first bit. And so, you know, this is how you can convert also these logical operations into just addition and multiplication, if that's, you know, easier to manipulate. All right, so now let's just see some simple relations between these elementary gates. So one thing you can do is, for example, you can ask, you know, maybe some of these gates are kind of redundant. Maybe you can implement them using the other gates. And so, you know, one thing you can do, you can always implement this OR gate, for example, using the AND gate by just negating the input and output. So if you do this, by negating the input and then again the output, you just end up, this AND gets converted to OR, and this is what's called in logic De Morgan's law. And similarly, if you put these knots on the other side, you can also convert, you can obtain AND from OR by putting these knots all over the place. And, you know, then that's also for this OR and NOT, it's meaningful to make these multi-input gates where you just kind of make a cascade of these 2 input gates, and you just kind of make a big cascade, as many as you want, and then you can just draw it as a single box with many inputs. And that's just for convenience. Okay, so now the question is, you know, okay, so we already saw we can eliminate, for example, the OR gate if we want to. You know, can we eliminate also the XOR gate, or, you know, what are the kind of relations between these, and can we somehow, you know, boil down to this gate set to some simpler gate set, and can we implement any computation in principle using this simple gate set? So that's kind of an interesting question to ask. So that's what we're going. So let's see, for example, how we can get rid of this XOR gate. How can we implement it using these other gates? And this is going to be the general recipe that we can use for implementing basically any Boolean function. Okay, so here, so remember this XOR gate is kind of like addition modulo 2. It has this Boolean truth table that looks like this. And so here's a general recipe that you can use to, well, I will explain for the XOR, but then you can generalize this. So first you need to observe where are the 1 entries here. So there are 2 1 entries here. And so what we're going to do is for each of these 1 entries, we have to do something special. So here, basically, there are these 2 special inputs that go to 1, and we want to single them out somehow. And so what we're going to do is, okay, so let's take this NOT gate. Let's put it here, and let's put another NOT gate here. Okay, so what we want to do is we want to have output 1 if the input is 0, 1. So 0, 1 means that we can negate x. So the negation of x, basically, if x is 0, then the negation of x is 1. And then if we take y directly like this. So imagine if we do this, and if we plug this into the AND gate, let's just take this guy and put it here. So now what comes out of this AND gate is going to be 1 if x is 0 and y is 1. So we really, out of all 4 possible input combinations, by doing this, we select this specific one. Okay. And now, similarly, we can also make another circuit that's going to select this one, the 1, 0. So we want directly x to be 1, so we don't negate it. And y we want to be negated, so we do this. And then we just put another AND gate here. And then that. So this is literally saying that x is 1 and y is 0. So that selects this third row. And then finally, so basically these two ones in this table here, they correspond to these two kind of outputs here. And we just want to say, and we just want to put an or at the end. We want to say, either we are, well, not either, but we are in this case, or we are in that case, right? So if we put the OR gate here, and okay, let's get rid of this, and let's just connect it like that. So now, so this circuit that I got here, it uses only not and an OR, and it has the same functionality as XOR. Okay, so basically, I just, for every entry in a truth table, I just put the right combination of negations and feed them into this AND. And then for every one here, I will have some specific entry that comes out here. And then I take OR, meaning that if any of these is true, then we are one of these cases when the output should be 1. And so that's why I put OR at the end. Is there any question about this this example? Okay, so now using exactly the same idea, we can actually compute any function. And by the way, also note that if you want, you can also get rid of these, either the AND gates or the OR gates, using this the Morgan's law. So you can always you can do some more massaging, and you can get either just AND and not if you want to, or you can just get OR and not in the end. So basically, either this pair is enough, or this other pair is enough. Okay, so let's see how we can do an arbitrary function. So now, if you have an arbitrary function, so Boolean function that maps an n-bit string to 0 and 1, think of this as detecting if this is a cat or whatever. And so, it's going to have a truth table, which is going to be very long, but basically for every input, so there will be 2 to the n inputs, you will have a value of the function, which is 0 or 1. So if somebody gives you the function, you can imagine they just give you this long list of zeros and ones. And now, given this truth table, you can use exactly the same procedure to compute this function using these elementary gates. And what you need to do is, again, you want to basically have, for every variable, you want to either have it original value or the negated one, so that you can sort of zoom into a specific row. And then you want to put some ANDs and some ORs at the end. So basically, what I'm going to do is have these NOT gates already here. And then, okay, let's pull out these original non-negated values as well. Okay, so now let's say, I don't know, let's start from the bottom, for example. Let's say we look at this entry here. And in this case, it has to be 1. So that's input of interest for us. So if we want to have 1 when all of these inputs are 1, then that's just a big AND gate without any negation. So basically, what we need to do is just take an AND gate and put it here and just have all the original inputs plugged into it. So if here, let's say this x1 is one of the original inputs, then one of these, one of those, and so on. And of course, then you can convert this AND with multiple inputs into an AND with just 2 inputs by using this cascade of gates that I showed earlier. So you can always just do this to boil it down just to 2 input gates. Okay, so now, so basically here we're going to have 1 precisely when all of these n inputs are equal to 1. So we're going to sort of select this particular row. Okay. So now, okay, so this is 0, we're not interested. So the next one we're interested is this one. Okay, so what we need to do is we need to have a combination of negations on these input bits such that we select this row. And so in this row is basically everything is 1 except this, the penultimate bit is equal to 0. So what we need to do is simply take another AND gate, and we need to negate this this penultimate bit. So we need to take this output here, and then everything else from the original as well. Okay, maybe I'll put it like that. So this just means that I'm copying this value of the bit. Okay, and so all of these guys, well, let's just connect it. Well, sorry. Let's just connect it nicely like this. And so these all we feed again into another AND gate. Okay, and so then for this AND gate, what comes out here is going to be 1 precisely when each of these is equal to 1, and when this penultimate one is equal to 0. Okay, and and so on. You go through this table and you select all of them. So let's say the remaining one is the all zeros, so it means you just need to take all the bits negated. So you basically you take all of these guys well, like this. Okay, now this is going to be very messy, but anyway, so you just feed all of these into another AND, and what comes out. So now you have for every row in this truth table where you have 1. You need to feed that into this final, or you want to say, we are in this or that or that or that case, and then what comes out is going to be the value of the function. Okay, so and this is exactly the same idea we use for this XOR, and so basically, in this way, you can in principle implement any function if somebody gives you this truth table. All right, so now let me briefly discuss the complexity of this procedure. So if we have an arbitrary Boolean function. It has n-bit strings as input, so the truth table will have 2 to the n entries. It's going to be really huge. And this circuit that we have, in the worst case, it can have 2 to the n ands, because we have, for every entry in this truth table that is equal to 1, we have to put an AND gate. So the number of these ands could be really large. And okay, and then you can do some kind of counting. You can say, okay, well, in general, it's going to be pretty bad. Well, maybe there will be some lucky functions where you have polynomial number of these gates, which would be sort of in computer science language, it means small or something manageable. But in fact, if you do some counting, you can argue that actually a negligible fraction of functions have a very short circuit that you can kind of represent it very concisely. So imagine maybe you just use 1 bit per gate, like you use 0 for the NOT and 1 for the AND gate or something. And then some extra information how they connect. But in general, you cannot really represent the function concisely. And so, basically, computer science is really the field of how to represent computations in a concise way. So how to compute something fast. You can compute anything in principle using this scheme, but it's going to be really huge circuit, going to take really long time or lots of resources to make. And you want to know which functions can you compute fast or with a little amount of resources. And so, for example, the parity function, if you compute it using this kind of generic method, it will have 2 to the n roughly gates, so it's going to be really bad. But you can make a cascade of these XOR gates. So the parity function is just the XOR of all the bits. And then, as I showed earlier, each of these XOR gates can be implemented using like 5 gates or something. And so this whole cascade will have like 5 AND gates. And that's, that's pretty manageable. And so basically, these kind of tricks of how to take some function and implement it in a very concise way is kind of what computer science study. And they want to basically understand for which problems we can have short circuits like this. All right, so now, so let's, so let me just say one more thing. So this is not obvious why we want to do this, but you could also ask, can you make a computation reversible? So basically, it's like you have a document and you want to press Ctrl-Z to go back to the previous thing that you had. You don't want to lose information, okay? And so here what's going to be useful is this Toffoli gate. So this is like a multiply controlled NOT gate. So it's going to flip this last bit precisely when both of these bits are equal to 1. Or algebraically, you can write it like this, that you are, flipping the bit, you are adding something, and you are adding 1, or this is like an AND, so meaning that, you flip this bit exactly when both of them are equal to 1. And so this Toffoli gate has the property that it's self-inverse, because if you apply twice like this, then because, anything plus anything is equal to 0 modulo 2, because, 1 plus 1 is 0, and 0 plus 0 is 0, then if you apply twice, then this term is just going to cancel out, and you're just going to get z back. And these first two bits didn't change; they just come out in the way they were. Okay? So it means this Toffoli gate is reversible. If you do it twice, you just get back the same thing. And so now let's see how we can implement these other gates in a reversible way. So what we can do is, so let's say we want to implement the AND gate. So we put the inputs x and y here, and we want to get the AND of x, y somewhere here. So what we can do is just put a 0 here. And okay, so the first two bits don't change. And so here what comes out is a 0 plus x times y, but x times y modulo 2 is just the same as AND, okay? So you can see this is a way to implement AND, and it's kind of reversible because the inputs are actually preserved. So you kind of, if you want to go back, you just want to erase in some sense this value. And similarly for NOT, you can imagine that you just put, let's say, 1s here. So then this is going to be flipped precisely when both of these are 1, and they are 1. So you just get plus 1. Okay, so because x times y, so here 1 times 1 is 1. So you're just adding 1, and that's exactly what the NOT operation is. And in fact, you can also copy bits. So if you have x here and you want to copy it, what you can do is you can do the following. You can just put 1 here, and then this what comes out here is going to be 0 plus 1 times x, and 1 times x is just x. So we get this. Okay, so like sometimes like in this circuit here, like in these locations, I needed to copy, and then you can just use this Toffoli gate as well for copy. And so it means that any circuit has AND, NOT, and copy. You can implement it using this Toffoli gate. And the reason it's reversible is simply that if you do it twice, you get back. So for example, if you have this kind of circuit of these Toffoli gates, if you want to invert it, if you want to kind of uncompute, what you need to do is just do these gates kind of in a reverse order. So basically, if you do this last gate, then you undo it. Then if you do this gate, then you undo that one as well. And then finally, if you do this first gate, then you undo that as well. And so this, this overall computation now amounts to doing nothing, because I sort of computed something and then I uncomputed it. Okay. And so what this shows is that actually not only anything can be implemented in principle, any functionality, it can be actually implemented in reversible way, and using only a single gate. Well, many copies of this gate, but this Toffoli gate basically suffices to do any computation you want in reversible way. Okay, so yeah, so okay, maybe I'm not going to talk about this, but you can also, so what happens here is that you have all these inputs lying around, and sometimes you might have some kind of intermediate results of computation lying around. Maybe you just want to get rid of it. So that you kind of get some clean output. And anyway, so there's a trick to do this. So basically, if you have your original input and then you have a bunch of the workspace that has some zeros and ones, and if you run your gate of Toffoli's, your circuit of these Toffoli gates, you might end up with some trash, but then you just can run this circuit basically backwards, and you can put an extra gate here, this control NOT gate, which is going to flip this final the final bit into the value of your function, or the result of your computation, and then you just run everything backwards, and you kind of uncompute. You get rid of all this trash and restore it like that. So this is kind of a neat trick that's used. It's actually used in quantum computing, for example. But anyway, so not only you can compute reversibly, but you can also compute reversibly, so you don't have any trash lying around at the end. You just have the original input, the value of the function you want to compute, and then the workspace gets restored to these whatever zeros and ones you had. Okay, so now let's move on to quantum computing. And as I said, the simplest thing before quantum computing is just probabilistic computation. And so what is probabilistic computation? Is just when you have some uncertainty about the information that you have, namely that you need probabilities to describe the state of your computer. And the simplest thing is just imagine you just flip a coin and it lands on one side or the other side, and you can just say, well, with probability half, it's lands on one side, let's say it's 0, and with probably half it lands on the other side and it's 1. Okay, so now a probabilistic bit is just a bit that has its values are 0 or 1, but they happen with some probability. And it's convenient just to represent it by a vector. You can just think it's in this, you can think of it as a table where we just collect these probabilities. We just write down, you know, this was the probability for 0, this was the probability for 1. And the constraints are simply these probabilities are non-negative and they have to add to 1. Okay, so like, you know, if you have 50-50, then you have half plus half and it's equal to 1. So that's possible state of your probabilistic bit. And in particular, just, you know, to make this clear, if you want to represent the value 0 of a regular bit, like of a deterministic bit, then it means it has 0 with probability 1 and 1 with probability 0. So it means that this vector, or this kind of little table of probabilities, represents 0. And if you have 1, it means you have 0 with probability 0, and you have 1 with probability 1. And so this other bit, other vector represents this kind of deterministic bit 1. Okay? So this, you can see, this is basically, this rule tells you how the deterministic values of the bit fit into this this probabilistic description. Like you just get these two specific standard basis vectors essentially. Okay, so now if you have 2 bits, then you know they are 4 possible combinations you could have. You can have 0, 0, 0, 1, and so on, and then you know therefore you need 4 different probabilities to describe what are the possible values of these bits, and then you would just make a little table of these probabilities. So you make a vector with 4 entries. And that, you know, that's this vector represents the state of these 2 bits. Okay. And so, by the way, if I have n bits, how long is this vector going to get? Can anybody tell? Like how many probabilities you need to describe all possible combinations of n bits? All possible values.
2 to the n, right?
Right, yeah. So you have 2 to the n probabilities. So the vector that you have would be very, very long. And by the way, you know, this is also what happens in quantum physics and quantum computation. And this is not, you know, people often say, oh, you know, we have exponential state space and so on in quantum computer. But in fact, you know, for probabilistic computation, you already also have this exponential state space. So this is not something that's unique to quantum computers. Okay, so now finally, let me just say maybe quickly, if you have 2 bits, how would you describe their joint state? So if you have 1 bit that has these probabilities and another that has those, then the probability to have them both in state 0 is just the product of these probabilities of having 0 here and 0 there. So basically P0 times Q0 is the probability that both bits are simultaneously 0, 0. And then similarly, the product of, you know, all other possible combinations, P1 Q0, P1 Q1, is going to give you the state of these joint, basically the joint distribution of these 2 bits. And this is in mathematics, I don't know if you're familiar with this, or also in quantum physics, this is called tensor product. And again, this is not anything specific to quantum physics, this happens, so it's just a natural way of combining things. It happens also for probability distributions. Okay, so now, and similarly, just like we did these operations on bits, you can also do them on probabilistic bits. So if you negate a bit, then these 2 probabilities simply exchange. So you just get them the other way around. If you do the identity operation, you just do nothing, so they remain the same. And, you know, and well, now actually, since we have these vectors and we're kind of acting on these vectors with these operations, these are logical operations, but we could actually turn them into matrices. So basically here, well, here nothing happens, so this is just the identity matrix. And here we exchange these 2 entries, and so you will get this matrix. And so in physics, this is called the Polyx matrix. Okay, so now, you know, you can also do, in fact, not only have a probabilistic state of your bit, but you could also do a probabilistic operation. You could say, well, you know, what about with probability Q, we negate the bit, and with probability 1 minus Q, we don't negate, we do nothing, right? So then what this means is that, well, you could write it like this, but then it's convenient also to use this matrix representation. So here you would have Q times this matrix, 0, 1, 1, 0, plus 1 minus Q, the identity matrix. And then you can just use, you know, just regular linear algebra, or just, you know, just entry-wise combine them. And so what you get is 1 minus Q, 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 1 minus Q, okay? And so then this matrix describes the, you know, flipping the bit with probability Q and not flipping it with probability 1 minus Q, okay? And then you can also do other things, like if you want to prepare, for example, the whatever bit you have, you want to kind of forget it and prepare it in state 0. So that's the first standard basis vector. So then you can, if you think a little bit, you can see that this matrix is going to do this because these probabilities add to 1. So this entry is just going to be the sum of them, and it's going to be 1. And similarly, if you have this matrix, it's going to prepare your bit in state 1. All right, so now, and then you can ask, well, what's the most general operation you can do on a single probabilistic bit? And it's going to be described by some kind of, combination of these matrices. And then you can ask, well, what's the most general linear combination of these matrices? What does it look like? And it's just going to have the property that so it's going to be some 2 by 2 matrix, has non-zero, non-negative entries. And these entries are going to, so the columns are going to sum to 1. And the reason for that is basically if you act, for example, let's say you act on the first standard basis vector, then what you're going to get out is just simply the first column. So definitely what comes out should be, if this is a valid operation on a probabilistic bit, what comes out should be a valid state of probabilistic bit, and so therefore this should be a probability distribution, so this should sum to 1, and this should also sum to 1, and then they should be non-negative. Okay? And you can argue actually that's all the constraints you need. Okay, and then similarly, if you act on 2 bits, well, then you have a 4 by 4 matrix because there are 4 possible values this pair of bits can have. And, and then sort of the meaning of this, for example, like, I don't know, if you look at this number here, this is simply the probability that your bit is going to be transformed from value 1, 0 to the value 0, 1. And again, this table should have the property that all the entries are non-negative and all the columns sum to 1. And so such matrices are called stochastic. So in general, you're just going to have a 2 to the n by 2 to the n stochastic matrix, and that describes the most general thing you can do on your n probabilistic bits.
I have one question. So earlier you talked about reversibility. So these matrices are not necessarily symmetric, right?
Yeah. So exactly. So this is not going to be reversible. So for example, this operation here that just erases the bit and prepares, kind of initializes in state 0, it's not reversible. Yeah. So this reversibility applies to deterministic computation, but not to probabilistic computation. But it's going to also apply to quantum computation. All right, so so then just as a quick example, so this C naught operation, that this control naught operation, if you represent it as a matrix, okay, I'm not gonna maybe explain it in detail, but it looks like this. So basically, these last two 0, 1, 1, 0. So that the meaning of this control naught was that we flipped the second bit if the first bit was 1. So it means, this is wrong, so this is 0, 0, 0, 1. So if basically if the first bit is 1, if we are in a bottom, then we just put essentially this naught matrix in here. Anyway, so this is something.
Good question.
Yeah.
Can you write this C naught as well as a tensor product of 2D matrices?
Yeah, so you cannot. What you can write it as is kind of. You cannot. You can write it as a sum of 2 terms. One term that sort of does nothing if the first bit is 0, and the other term that does that flips the second bit if this is 1. But yeah,
so it has sort of rank 2.
Yeah.
Okay.
And sort of the meaning of this is that sort of it's really a joint operation. It's not you are not acting independently on these 2 bits. Yeah. By the way, independent operation would just, well, I guess diagrammatically would look like this, but mathematically you would write it as a tensor product of 2 by 2 matrices.
But can you maybe write it as a direct sum of matrices?
Yeah, so it is a direct sum, exactly. So it's a direct sum of the identity matrix and this Pauli X, or this negation matrix. And in quantum computing, you would write it like this. So I'm not going to explain the bracket notation, but anyway here, and then this X matrix. So basically you could write it like this for those who are familiar with this notation. So you have these 2 terms. So this just means if the first bit is 0, you do nothing, and if the first bit is 1, you negate the last bit, the second bit.
So sort of C naught correlates the bits.
Yeah, it is somehow. Yeah, it's really acts jointly. Okay, so and also in quantum computing, this is called an entangling operation, that sort of you can create entanglement between these 2 bits. Okay, so now let's see how does this relate to quantum bits. So basically, the difference between probabilistic bits and quantum bits is really small. So, you know, the probabilistic bits are just described by these 2 numbers that are non-negative and sum to 1, and you know, all possible values of a probabilistic bit are just correspond to this kind of line segment here. So this was the deterministic value 0, and this is the deterministic value 1, and then this would be like, you know, 50-50 or something, or half and half, and then, you know, anything in between. And quantum bit, so okay, I'm just going to simplify things. I'm just going to use real numbers, but it's just also a pair of numbers, and these numbers can be negative, so that's one difference. And the normalization is not that the sum of the numbers is 1, but the sum of squares is equal to 1. So this is just the equation for the circle, basically. And, you know, in general, you have to use complex numbers, but, you know, for the purpose of this talk, it doesn't matter. And so you can see there are 2 differences. The one difference is these numbers can get negative, and the other one is this normalization. So basically, you know, if you compare it to these probabilistic bits, they kind of look like this. And so there's this little kind of bulge out, so that's like one small difference. And the other difference is that you can go negative. You can sort of go all in this kind of region. And so there's this little bulge that has to do with the Born's rule. So this normalization basically is what's called Born's rule. And the fact that you can go negative means that you can also sometimes things can cancel out. So not, you know, when you add these numbers, they can not just amplify like probabilities, they always add and they become bigger. But because they are negative, they can also cancel each other out, and that's what's called interference in physics. And so that's, you know, that's basically, these are the only 2 differences essentially. All right, so now what's the more general operation on such a quantum bit? So remember, for a probabilistic bit, you have this 2x2 matrix where this is a probability distribution in every column. And in case of quantum bits, you basically this has to be an orthonormal basis. So this is a base in 2 dimensions, and these vectors should be orthonormal. And kind of, you know, intuitively, this matrix, what it does in case of probabilistic bits, it should map somehow this line segment onto itself, or maybe onto some smaller subset, like maybe, you know, an operation like this. But this quantum operation, it should map this circle basically to itself. And the only thing you can do is just you can rotate this circle basically, or you can choose some line like this and you can reflect it. But again, for the purpose of this talk, I'm going to assume that you can only rotate because, you know, in reality, you have actually complex numbers, and then this actually is not a circle, but it's a sphere, and then rotations of that sphere corresponds to what you can do with a full qubit. All right. Now, so then, you know, if you rotate by some angle alpha, then the operation, this 2x2 matrix, is just going to look like this. It's just going to have some sines and cosines. Okay? And basically, for the purpose of this talk, this is the most general operation you can do on a single quantum bit. All right. So now, so what I want to explain now is, you know, what I showed you earlier was this idea of you can take any computation you want, any Boolean function, and you can break it down into these AND and OR gates. You can kind of compile it down into these elementary building blocks. And we want to do something similar quantumly. So we want to take, you know, a big matrix. So in general, if you have n qubits, you're going to have 2 to the n by 2 to the n matrix. And you want to take this big matrix and somehow break it down into elementary matrices that are like, you know, 2 by 2 or something like that. And so I'm going to explain how you can do this. And the idea is very simple. So basically, it's just this equation here. So, you know, so let's just look at a simpler question. Let's say we want to prepare an arbitrary state on our computer on this qubit, or actually let's consider unpreparing it, sort of mapping all the information back to 0. So let's say, you know, just mapping it to this first standard base vector. So if we have a state that looks like this, that has some cosine alpha and minus sine alpha, I mean, I guess it would look something like this. If you want to map this vector back to 1, 0, oh no, sorry, actually this should be, if the first component is cosine and this is minus sine, it should look like this. If you want to map it to the first standard base vector, so that's just the x-axis basically, you just need to rotate by angle alpha. And that we can do by this u alpha operation, because, you know, that was just rotating well, I guess, okay, this I wrote it the other way around, but it rotates by angle alpha. Okay. Okay, so now by just by rotating by the right amount, we can map any point on a circle just to the x-axis basically. And if this vector was not normalized, if we had actually some completely arbitrary two numbers here, we can always find some angle which is going to have to do with the arctangents or whatever between these two things. It's just going to have to do with the angle this arbitrary vector makes with the x-axis. And just choosing that angle here, we can always rotate it to some vector of the same norm that points horizontally. Okay. So in other words, if we have an arbitrary vector like this with some two unknown entries, we can always zero out the second entry. And similarly, if we have maybe a larger system, well, with 3 or 4 or whatever entries, we can first zero out the last entry like this, and then we can zero out this entry here like that. So basically, what we need to do is we simply need to be able to act. So if we want to get a 0 here, we need to apply some right rotation here, and then we apply the right rotation here to get this 0 here. Okay. So by using some kind of cascade of these rotations at the right places, we can map anything to just something and then zeros here. Okay, and this this general rotation is just going to look like this. It's going to have once on diagonal, so it's very close to identity matrix. But then at two specific locations where we want to do something like here, we're going to have this kind of rotation matrix here by some angle alpha. Okay, so at some coordinate k. So I'm going to call this u alpha k. So we rotate by angle alpha at coordinate k. And so we just want to apply a sequence of these, and then we can map anything to the essentially first standard base vector, up to some normalization. Okay, so now imagine you have an arbitrary operation, and so for simplicity, I'm going to look at 3 by 3. But if it should be on qubits, it should be like 4 by 4 or something. It should be a power of 2. But okay. So let's say you have arbitrary rotation matrix that looks like this, and you want to somehow kind of simplify it. You want to just put bunch of zeros. So what you can do is you can just choose the right rotation angle here, and just act on these last two components to get a 0 here. Okay. And then you can act on these two components, again, by the right angle, and then you get the 0 here. And of course, this 0 is not going to be messed up because you just acted here. So you basically, when you act, basically, when you act like that, you will be doing some operations in the rows, essentially. Okay, so now at this point, you have two zeros here. And what you can do is, again, act on the last two rows. And because you have zeros here, they are not going to change. And you can get another 0 here. Okay, so basically at the end of the day, you can get the whole lower triangle of the matrix. You can make it all zeros by doing a cascade of these rotations with the right angles. And now, because if this initial operation was a valid operation on a quantum computer, then the final one should also be, because these were valid operations that you did. And then a valid operation should have an orthonormal basis here. And so for these two columns to be orthonormal, actually, there should be a 0 also here on the top. You should actually have a 0 here. And then for again, for the first one and this one to be orthonormal, there should be 0 here and there should be 0 there. And so in fact, basically, you can argue what you should get is all the off-diagonal terms, not just the bottom, but also the top. You get them for free equal to 0. And on a diagonal, it should be just once, because these should be normalized vectors. So I'm glossing over some technicalities, but it will essentially be like this. So it means that if you have any operation, if you have this operation Q, you can multiply by U1, U2, U3 with the right angles, and you can bring it down to identity matrix. And now if you just multiply by U3 inverse on both sides, then you can cancel this out, and you get U3 inverse there. Then you multiply by U2 inverse on the left, and you cancel this one out, and you get the U2 inverse here. And then you finally multiply by U1 inverse, and you get this. And so, what we have done here is basically decomposed an arbitrary operation on our qubits into a sequence of these two-level operations that act just on two levels at a time. Okay. All right. So now, so now we would like to break this down even further. So it means that basically we could do any operation whatsoever just using these kind of operations that have this, it's almost like identity matrix, but has this little rotation here. So we would like to now break this one also down into smaller things. And now note that if this k is maximal, so if you push this little 2x2 block at the very, very corner, then you're really going to be acting only on these 2 bit strings non-trivially. So basically on all the other bit strings, you're going to act as identity. So all these other, if you have 4 probabilistic bits or 4 qubits, then all these other possibilities are not going to change, because this kind of upper block here is just identity matrix. So that's how you act on these guys. And then you do a little rotation between these guys. And that just means that actually what you're doing is you're doing a little rotation on the last qubit if the first qubits are equal to 1. So it means actually pictorially this gate here, that looks like this big matrix, you can represent it like this. It means that, this control means that if this is equal to 1, you're doing something, and then when you connect them, it means that it's like an AND. It means that, if all of them simultaneously are 1, then you're doing some rotation on the last qubit. Okay, so basically this matrix corresponds to this kind of picture in the circuit. And now if you want to implement this, what you can do is as follows. You can just put a bunch of these Toffoli gates that we had earlier when we were dealing with reversible computation. And so the Toffoli gate, what it does is simply as follows. So if you have x, y, and z, what comes out here is x, y, and then z plus x times y. And so it means that, for example, if we make this kind of circuit, what comes out here, if this was 0, we're just going to get the product of x1 and x2. And now, so we have here the product of x1 and x2, and then we kind of multiply it with x3. So what we have here is x1, x2, x3. And the product of x1, x2, x3 is just the AND. So it's 1 exactly when all of them are equal to 1. Okay, so it means that we have computed here AND of the 3 inputs, and then we just do this controlled rotation with just a single control. So if this is equal to 1, we do the small rotation. And so this just amounts, we essentially, instead of saying we compute AND of these and rotate only if this AND is 1, we can do this by some extra gates essentially, and then we just only have one control because we have the value of AND essentially stored here. And then this is just to uncompute, so we return everything back in the original state. If this was some kind of workspace that has zeros, we want to have them back to zeros. And so it means that, if we have this multiply controlled rotation on 1 qubit, we can break it down into a bunch of these Toffoli gates that act on 3 qubits, and then this control rotation that acts just on 2 qubits, and it controls on 1 qubit and rotates on 1 qubit. And then you have, if there were n inputs, you will have roughly n gates on one side and n gates on the other side. So this is kind of, there's not too much overhead here. Okay, so then what remains is to just break down, so what remains is also to show how this can be done, this kind of breaking down of this multiply controlled unitary, but if this 2x2 block was somewhere else. So remember, in general, we need operations like this, where this block could be, you could kind of shift it up and down. It could be anywhere. It's acts so non-trivially on any 2 consecutive rows. And so to do this, the trick that you can do is as follows. So let's say these were the 2 consecutive indices. So like, I don't know, I guess this would be k equals 3 in binary, and this would be k equals 4. So what you can do is, if you want to have this block at basically location, so if you want to implement alpha 3, rotating by angle alpha at kind of location 3, we can do as follows. So basically, since these are 2 consecutive positions, then these 2 last bits are going to be different. And what we want to do is we want to just map back to this original case that we figured out, where, so the thing that we had here, when this block was at the bottom, we have a bunch of 1s here, and then this last bit was arbitrary. So we want to somehow simultaneously map these 2 things to this case that we know. And what we can do is we can just use these C-NOT gates first. So basically, these controlled NOT gates, they act on these 2 bits if the last bit is 1. So it means that in the second string, nothing's going to happen. So we get exactly the same string back. And in the first string, this is 1. And so these get flipped. So we get 1 here, and we get 0 here. Okay? So basically, in this way, by using this difference in the last bit, we can make these strings exactly the same. And then what remains to be done is just when it's 0, like this here, or when it's 0 here, we just need to negate to get ones. So if we want to get to this kind of case, we know. And then these were in the wrong order, so we can also negate this one. So we get this. Okay. And so the general circuit for basically getting any k, not just the biggest one, would look something like this. So you need first a bunch of these C knots. So okay, let me just copy these guys here. And I'm putting also everything at the end because I want to uncompute. So so these two C knots, they just make sure that these bits, they just implement this first step to make sure these bits are all the same. And then we need a bunch of these NOT operations to just do these negations. So the circuit will look something like this. And I'm putting also everything on the other side to just uncompute. Okay, so then the overall circuit looks like this. And so what this lets you do is simply to implement use this multiply controlled rotation that we already know how to implement a completely arbitrary one. Okay. All right. So now, if you cascade all these things together, then what this amounts to is you have an arbitrary 2 to the n by 2 to the n matrix that describes some quantum operation on n bits. You can first break it down into roughly 4 to the n two-level operations. This was just this kind of, remember this getting these zeros at the bottom in this triangle. And then, of course, what we need to do is we need to break down each of these two-level operations further. We could do this into this multiply controlled rotation and this Toffoli gate. And then what I showed just now is that you can break down this multiply controlled operation into just a singly controlled one and a bunch of controlled knots and regular knots, so like this circuit here. And then finally, I'm not going to say how to do this, but you can also break down this one into just control knot and just a single qubit rotation. And this 3-qubit operation, this Toffoli gate, you can also break down into these. And so what it means is that anything, any huge 2 to the n by 2 to the n matrix, by going through to this procedure systematically, you can always break it down into these elementary gates that act just on a single qubit and rotate by some arbitrary angle, and this 2-qubit gate, this C0 gate. All right, so this kind of shows some kind of a completeness. So let me summarize. So basically, what I told you is sort of this kind of completeness result, that if you have any n-argument Boolean function, you can always break it down into logical gates. And of course, the circuit is going to be huge. In general, it's going to have 2 to the n gates, but they all are kind of simple. They act on just 1 or 2 bits. So it's just an AND gate or NOT gate or something like that. And similarly, in quantum case, if you have an n-qubit operation, it's described by some huge matrix, but you can always break it down into some elementary gates, and these gates just act on 1 or 2 qubits. And the 1-qubit gates are just these rotations by arbitrary angle, and 2-qubit gate is just this once C0 gate. And so, the practical implication of this is that if you want to build a quantum computer, you basically need to be able to do this arbitrary single qubit operation and then this control NOT gate. But you could, there could be some other things depending on the platform. Maybe you have some other gates that are easier to do, but you can then always kind of cross-compile between the gate set that you have and this other gate set.
Question?
Yep.
You discussed briefly something in between the Boolean function and the qubit, which is the probabilistic bit.
Right. So
does the completeness also hold for probabilistic?
Yeah. So
stochastic operators.
Yeah, that's a good question. Yeah, basically, I think this. I haven't thought about this, but I think the same strategy works. So basically, but yeah, you have to be more careful.
It's not time reversible, as you know.
Yeah. I think you would have to go the other way. You would have to start with the identity operation, and then you do a little 2x2 sort of small stochastic operations, like small, well, not rotations, but sort of smearing out. And then you would kind of build your matrix up. So you would start with identity matrix and you put the right entries. And I think the same idea should work as well. All right. Yeah. So then also, well, let me quickly say that what this means is that, if you, in particular, we can, what this also means is if we have any computation, any deterministic computation like and ORs, we can implement it reversibly using these Toffoli gates. And once it's reversible, this Toffoli gate is also some gate you can apply on a quantum computer. So it means that, you know, quantum computers can do everything that a regular computer can do, because, you know, you can make the regular computer reversible and then you can make it quantum basically. And also the other way around. So if you have a quantum computer, then, well, this is not as easy to see. You can describe all these numbers that I'm using, all these calculations and all this matrix multiplication and all that. You can sort of implement it using logic, like on a computer, on a regular computer, on some MATLAB or whatever. And, you know, you can draw some huge circuit that's going to simulate your quantum computer. But of course, that circuit is going to be really big. And because the state of the quantum computer is already of size 2 to the n, you will have to have a circuit that's at least of size 2 to the n. So basically, you know, if you want to simulate quantum computer in some kind of trivial way on a regular computer, you will have the exponential overhead. And so, you know, that's sort of why it's interesting to build quantum computers, because it's not clear how to simulate them, but they can do interesting things. And, you know, the interesting things they can do, for example, is factoring numbers or simulating quantum systems. So that was like simulating quantum systems was the main motivation, for example, for Feynman to consider quantum computers. And so the quantum computer sort of naturally, because it's quantum, it can simulate any other quantum system. But, you know, if you want to simulate the quantum system classically on a regular computer, it's not clear how to do this, and you will have this kind of exponential overhead in general. So yeah, so that's all I wanted to say. Sorry if the end was a bit rushed, but yeah, I hope this gives a bit kind of like a bigger picture of how, you know, how you can think about quantum computers, that it's kind of like a probabilistic computation, but with some negative numbers basically normalized with a 2 norm instead of 1 norm. And, you know, and that any computation can always be broken down into these elementary steps. Just kind of the main message.
Yes. Thanks very much.
So we already had some questions, but if there are more questions, comments.
Yeah, I mean, feel free to ask.
Yeah, this is going to be quite a vague question because I'm not sure on how to string it together. So I'm mainly working in complexity science. We're working on complex systems, which also relates to like finding mechanisms and how circuitry binds together to produce some outputs. And quantum mechanics have also kind of fascinated me because it's sort of has a lot of symmetries with how you think about what the nature is of this relationship. And I'm wondering if this sort of Boolean type of reasoning can help people in understanding and decompose complex interactions into more elementary parts.
So, okay, so, you know, what I explained is nice in principle, but this decomposition is always going to be huge. It's going to be of size 2 to the n, right? And so if you have sort of some kind of system has n bits or n ingredients, if n is like 100 or something like that, then the circuit you're going to get is going to be so big that you can't even write it down, basically. Yeah, I think it's really, you need to know more about your complex system. I think one thing that is really a useful tool that's used in physics and also in quantum computing is this idea of tensor network. And it's basically, it's kind of like, you can think of it as a little bit like, it's kind of like a logical circuit. So you can imagine you have a bunch of boxes and you connect them together with some
The screen is not shared, by the way, right now.
Oh yeah, sorry, I forgot to share. Yeah, sorry. Yeah, I stopped sharing. Yeah, okay, let's share this again. Yeah, so imagine you have some boxes and you can connect them with some wires, and you know, and what these wires carry now is not going to be just values like 0, 1, some logical values, but they are going to be sort of well, how to say this? So this is like a linear algebraic structure. So basically, imagine these are indices I, j, k. And so if you have just a box with one index like this, then you can think this is as a vector that has some entries vi. And this box just, imagine this box is just some kind of procedure that given I, it outputs this vector entry vi. And if you have a matrix, it's just a box with 2 inputs like this, you know, one for the row index, one for the column index. And if you multiply a matrix with a vector, then you draw a picture like this. If you multiply two matrices, you draw a picture like that. And what comes out is just another matrix. And I think sort of, you know, and then you can have, like, if you have some complex system, then you can have a bunch of these things connected together in some arbitrary way. And each edge here represents essentially some kind of contraction of index or some kind of summation. And each of these boxes essentially carries a bunch of numbers. So let's say if everything is binary, then there will be 2 to the 3 numbers sitting inside for all combinations of these inputs. So if you have a box with just 2 outputs, it will look something like this. And I think, for example, this kind of idea of tensor network is very useful for modeling systems, both in quantum physics and quantum computing, because you have this exponential blow-up only is inside each of these smaller boxes. So maybe, you know, this box has 3 legs, or 3 of these kind of you know, lines. So you need like 8 numbers to describe fully what's inside this box. But then if you connect them in some kind of big network, this network would have like n edges coming out. And so instead of having one box with many edges coming out, where you would need 2 to the n numbers, if you know some structure of this thing, if you break it down, you'd have these smaller boxes that have just smaller, like 8 numbers or something. And so this idea is used, it's very powerful, it's used a lot in condensed matter physics and, I don't know, high energy physics and quantum computing and so on. I think this is something that could be used in principle to model different systems. It doesn't, you know, these could be probabilities, and then it's like a probabilistic system, and then this contraction corresponds to some kind of probabilistic process. But yeah, I would say I think that this is maybe more useful. But this, you know, but always what you need to know is something more about your system. Like, it's kind of like, you know, what I showed was a generic method how to decompose any function, but it's in a very inefficient way. And if you have more information about this, then if your function, then like if your function is built out of smaller blocks, and each of those blocks you know how to efficiently decompose, then you should just, you know, kind of do that instead of using this generic procedure. And yeah, so I hope that helps a bit.
Yeah, it does. It's the reason why I asked is that, like, for sometimes you just don't know, right? And you have no real, like,
yeah, you
thematic
have
approach
some
to
kind of guess basically, or some.
Yeah, exactly. Okay.
Yeah, because if you don't know anything, then, you know, then your system could be doing anything. It could be arbitrarily complex, and you might need like 2 to the n numbers to describe it.
Okay, thanks.
Okay, more questions? Comments?
Just maybe I have a sort of general question about your last remark. You said something like that the quantum computer could help in simulating quantum systems.
Right.
But at some point, let's say, like, the most accurate simulation of a quantum system is to just really build the quantum system. And so is there like a demarcation between doing a quantum simulation or doing an experiment on a quantum system?
Yeah. Well, that's a very good question. Yeah, I think the reason you might want to build a quantum computer instead is because it's universal. So namely that, you know, just like, you know, if you want to make an Excel spreadsheet, you wouldn't build the Excel computer, and if you want to do the Word, then you build the Word computer, and if you want to do email, you do the email computer. You know, you just have one computer that's universal. It can do anything. And the same idea is for quantum computers. That, like, basically what I showed you is that, you know, you can decompose any interactions essentially between a physical system that you want into these elementary operations, and then you could just run them on a quantum computer. And so then, instead of doing many physical experiments, which might be costly, if you had one universal quantum computer, then you could run all these experiments. Essentially, you could simulate them on your quantum computer.
Thanks.
Okay, if there are no more questions, then let's thank Maris again. And this ends the last deep seminar of this semester. Okay, let me